Hello everyone. So this is Orko Das here, and we are going to discuss the toughest problem of CMI 2023 this year. So the exam was held last week. So today is 14th of May, and today we have our ISA exam, and it's currently 3:30 in AM. So whatever you say, late night or early morning. So let's do some maths, late night maths. And yeah, so first of all, those who are going to sit for the ISA exam, so all the best to you all. And for the CMI exam, yes, like every year, this year it was not offline; it was held online, and so I just got the questions just I mean, 3 days back. So I have solved the subjective questions. I still don't have the objective ones. If you have the objective questions, you can send it to me. And yeah, so I've solved all the subjective ones. So I'll be going to post the solutions to all of them. And so I'll be starting with the toughest one, which was the sixth problem, according to me. And it was a number theory problem, and that's one of my favorite topics. So yeah, so let's get started with it. And I'm going to post the solutions with a decreasing in the level of difficulty of the questions. Like I mean, almost all of you have solved problem 1, 2, or maybe 3. So the thing is that problem 6, which I mean, most of the people haven't been able to solve. The problem was given, and it was said that if you can solve it directly, so solve it. Otherwise, for some partial credit, you can solve some of the parts that were given, but from those parts it was not very direct or intuitive that how we can reach the final conclusion. So it was just for the partial credit, but yeah, but we are going to solve directly without using the sub parts or anything. So yeah, let's get started. So I'll first write down the problem. So the problem is saying that, so this is CMI 2023. So I'm posting the solutions because every year, CMI hasn't posted the solutions yet, and the students, most of the students do want to know how we can solve such problems. Yeah, so CMI 2023 B6, there are two parts, part A, part B. So this is part B, last problem, sixth one. So it's given that for every a naught, sorry, for every integer a naught greater than 1, define the sequence a naught a1 dot 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 by a n plus 1 is equal to root over of an if root over of an is an integer and a n plus 3 otherwise. Okay, so whenever we get a perfect square as one of the terms in the sequence, so the next term will be nothing but the root over of it. Okay, so this is for each n greater than equals to 0. And now it said that let S denote the set of distinct numbers in the sequence a naught, a1, and so on. Now, find all values of a naught for which the set S is finite. Okay, so basically we have to figure out the integers I mean a naught integers which we should start with, so that the number of distinct terms in the sequence will be finite. Okay. So now, those who haven't solved this problem yet, or those who are just looking at the problem right now, so just pause the video, and I request you to first try it out on your own, and then you can look at the solution. Okay. Yeah. So let's get started with the solution. So first of all, my claim is that this set S is finite if and only if 3 divides A naught. Okay, so this is our claim. Now, how are we going to approach? So in short, we are going to approach the problem we are going to show that if I start with A naught, which is divisible by 3, that means A naught is an integer. So it could be either 3k or 3k plus 1 or 3k plus 2. So if A naught is of the form 3k, then I'll show that the set S will be finite. Second step, I'll show that if A naught is of the form 3k plus 1, then again my S will be infinite. Okay. And also, if my S is of the form 3k plus 2, A naught is of the form 3k plus 2, then also I'll show that my set will be infinite. And so I'll be done with the proof. Okay. So one of the step is very easy, the 3k plus 2 part. Okay, so let's get started. So step 1 is to show that let us prove that if 3 divides A naught, then S is finite. So basically 3 divides A naught means A naught is of the form 3k, where k is an integer greater than or equals to 1. So what we are going to do is we are going to induct on k. So first of all, just notice that if A naught is 3, then what is the sequence that is getting formed? So the sequence that is getting formed is 3, then 6, then 9, and then since 9 is a perfect square, so the next one will be 3, and again, it just repeats. So the number of distinct elements in this sequence is basically 3. That is 3, 6, I mean 3 distinct elements, so which are 3, 6, and 9. So if A naught belongs to 3, 6, or 9, then that implies S is nothing but 3, 6, 9. So now we'll assume the result is true for A naught belonging to 3, 6, 9 dot 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 till 3k minus 3. And let A naught be equals to 3k, where k is greater than or equals to 4. Because why I'm taking k greater than or equals to 4? Because I'm already done for k equals 1, 2, and 3. Okay. So now there are two cases. That is because now in the first step there will be two cases now. That is, one is our A naught is a perfect square or it is not, because we have to deal with these two cases here, right? So because once when it's a perfect square and once when it's not. So first let's take that our if 3k, that is our A naught, sorry, we took a naught as 3k. So if 3k is a perfect square that is equals to m square, then m is divisible by 3. So that means 3 divides m. And so what we have is, that is, then the next term, a naught is 3k, which is a perfect square, which is m square. So then a1 will be equal to m according to the definition of the sequence given. And since 3 divides m, so m will be of the form some 3l, where l is strictly less than k. And by, again, our inductive assumption, the set will be finite, as we have assumed here. Okay, and since our l is less than k, so we are done by inductive assumption. Okay, so by inductive assumption, the set a1, a2, dot 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 is finite. So this was easy, right? So now, as I said, there will be two cases. The starting element is a perfect square or not. So that's the hardest part. So if the starting element is not a perfect square, so if 3k is not a perfect square, then 3k will lie strictly between 3m minus 3 whole square and will be strictly less than 3m square. Now here is the thing, that is, you would ask that why aren't you taking two consecutive squares? I mean, naturally what we do, whenever we have a non-perfect square integer, we can easily say that it lies between two consecutive perfect squares. So, but here you would say that these two are not consecutive perfect squares, right? But you see that I am not worried about two consecutive perfect squares. I am worried about two consecutive perfect squares which are divisible by 3. Okay, so I mean, the two consecutive perfect squares which must be a multiple of 3. Okay, so because I know that, I mean, even you can see from here also, that is, if there is a term where we are getting a perfect square, so then there it I mean, it will be divisible, that suppose whatever that is some b square or whatever, so that b will be divisible by 3. Okay, so that's why we need two successive squares which are a multiple of 3. Okay, so for some m greater than 2 or greater than equals to 2. Okay, so then the next values, that is a1 will be 3k plus 3, then a2 will be 3k plus 6. Okay, and so on and so forth. We will be getting a 3m squared. It's not 3m whole square, it's just 3m squared minus k minus 1. So this term will be 3k plus 3m whole squared minus 3k minus 3. Just observe the pattern, what is happening here with a1, a2. Okay, so this is nothing but like 3k plus 3 into 1, then 3k plus 3 into 2. So that means here also it will be 3k plus this index multiplied by 3. Okay, now you would definitely ask that how do we you just keep you just keep on adding this 3 3 3. How do you know that none of them is a perfect square? Okay, because if someone is a perfect square in between, so then it would just go into root over, the next term would be just root over of that, and things would change. Okay, but what I'm doing here is all I'm doing is adding this 3 constantly, right? So here's the thing, that is, I mean, all the terms are divisible by 3, and I have started with 3k. So the next perfect square is 3m square. Okay, so then the next perfect square, basically, which is, sorry, not, I mean, the next perfect square. The next perfect square, which is divisible by 3, is 3m square. So since every term is divisible by 3, so that perfect square will also be divisible by 3. So that means the next perfect square which comes into our scenario will have to be 3m square. Okay, so I mean, it can come or may not come. So let's see. But the thing is that yes, I mean, no other perfect squares between 3k and 3m square can't come because they are not divisible by 3. And this is, if you simplify this out, so we are getting 9m square. So here, okay, so yeah, 9m square minus 3. I think I have correctly, yeah, fine. So this is what is coming, this term 3a. Okay, so now the next term, what will be the next term? So the next term will be added, we will be adding 3 again because this is still not a perfect square. So 3m square minus k, this will be 9m square minus 3 plus 3, and so which is basically 3m whole squared. Okay, and now, okay, so this is the next term, and now note that we are finally getting this perfect square here. Okay, so what will happen is that now again, what will be the next term? That is 3m, correct? So then let's see something, that is 3m. I'm claiming that 3m is less than or equals to 3m minus 3 whole square. Okay, so this is this perfect square. Okay, so whatever be the root over of that is 3m, the next term, so that will be lesser than or equals to 3m minus 3 whole square. Okay, so you can also very well I mean, we are going to prove it, plus you can also very well understand that since okay, first let's prove it. So so this is our claim, and this is if we expand, so 9m square minus 18m plus 9. Now if we just take everything on one side, so we are going to get, this is 3 is getting cancelled out, and the 6 7 m is less than equals to 3m square plus 3. So if I'm able to prove this, so I'll be done. Okay, so then I know that 3m square plus 3 is strictly greater than 9m. Why? Because for m greater than 3, or let's take greater than equals to 3, this is strictly greater than, because 3m square is 3 into m plus 3, so which is greater than 3 into 3 times m plus 3, and so which is greater than, strictly greater than 9m. So this is greater than equals to, and that is strictly greater than 9m. Okay, and so this is greater than 7m, and so we are done. So this is proved, and so this is true. My claim is true. Okay, and so we have 3m, which is less than equals to 3m minus 3 whole square, which is strictly less than 3k, and m less than k. And so by the inductive assumption, the set a 3m square minus k, a 3m square minus k plus 1, and all those till a naught to, okay, whatever. So that set is finite. Okay, so the basic thing is that once I reduce it to something lower in here in our assumption, so once a naught boils down to here, so then we can easily say by our induction hypothesis that S will be finite. Okay, and we are done for this part. So that is, we all we have proved is that S is finite when 3 divides a naught. Okay, so we have proved this part. So this is done. Okay, now all we are left is for 3k plus 2 and 3k plus 1. Okay, so let's do the easier one first. Step 2, that is, assume a naught is of the form 3k plus 2, where k is greater than equals to 0, is an integer. And now the very first thing that you should know is that if I divide any perfect square by 3, so the remainders are going to be 0 and 1. Okay, so that is like if n is congruent to 1 modulo 3, then n square will be congruent to 1 modulo 3. If n is congruent to 0 modulo 3, then n square will be congruent to 0 modulo 3. And if n is congruent to 2 modulo 3, then n square would be congruent to 1 modulo 3. So in all the cases, we can get either 0 or 1 as the remainder. So now, since a naught is of the form 3k plus 2, so it itself cannot be a perfect square, because when divided by 3, we are getting a remainder of 2. So now that means we will add 3 with it to get the next term. Now again, if we are adding 3 to it, so again the next a1 will be again congruent to 2 modulo 3 basically. So again a1 can't be a perfect square, and so on and so forth. So none of the terms could be a perfect square, and so this plus 3 plus 3 plus 3 plus 3 would just continue, and S would be infinite. So when a naught is of the form 3k plus 2, we are done. S is infinite. Okay, so for 3k plus 1, I had to go through a lot of calculations and a lot of cases. So please bear with me. But yeah, it's a solid proof. So we will assume that a naught is of the form 3k plus 1. K is greater than equals to 1. So again, we'll prove by induction on K. We'll induct on K that the set is infinite. Okay, so here again, we are going to prove that the set is infinite. So let K be equals to 1. Then you know that A naught is equals to 4. Okay, and A1 is equals to 2 because A naught is 4. So the next term would be square root of that. So this would be equals to 3 times 0 plus 2. I mean, we can see it in that way, and so on. So then you can very well see that since as one of the terms becomes of the form like, I mean, giving a remainder of 2 when divided by 3. So it's not being a perfect square. The next term would be just plus 3. Again, the remainder would be just same when divided by 3, that is 2, and so on and so forth, and it continues. And if the starting element is 4, so it's a never ending thing. So S is infinite. Okay, so let's go with k equals 2. So k equals 2, then we see that a naught is equals to 7, and we get the sequence 7, 10, 13, 16, 4, because 16 is a perfect square, so we get 4, then 2, and so on. Again, by step 2, we can say that S is infinite, because once we get 2, which is basically an element, when divided by 3, the remainder is 2. So again, the same thing continues, okay? And so this shows that we will get an infinite set S when, so this shows that we will get an infinite set S when A naught belongs to 4, 7, 10, 13, 16. And now our induction hypothesis is coming into the scenario. So we'll assume that the result is proved or true, whatever, for A naught belonging to 4, 7, dot, 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 3k minus 2. And let A naught be equals 3k plus 1, where k is greater than equals to 6. Okay. Otherwise, like for lesser case, we are done. So now again, the same approach as we did in the first step. That is, there are two things. That is, this 3k plus 1 is a perfect square or not. So if A naught is a square, then 3k plus 1 is equals to p square. And yeah, so let it be some p square. And so 3 doesn't divide p. Okay, and yeah, so p is not divisible by 3, as we can very well see. And so we can say that p is of the form some 3l plus r, where r belongs to 1 or 2. So r is either 1 or 2. Okay, so it can't be 0, because 3 doesn't divide p. So now again the same thing, that is, if r is 2, then we are done. So then a1 would be of the form 3l plus 2, and again by step 2, S would be infinite. So we are done here for this r equals 2. So the main part is for r equals 1. So S is infinite for this case. Now let's go to the next page. So yeah, let's take if r is equals to 1, then 3k plus 1 is equals to 3l plus 1 whole squared. Okay, because p, we are taking it of the form 3l plus 1. Okay, and 3k plus 1 is nothing but p squared in our first scenario. So 3l plus 1 whole squared, which is nothing but 9l squared plus 6l plus 1. And so we are getting k equals 3l squared plus 2l, and which is strictly greater than n. Now, since a1 is equals to p, which is 3l plus 1, l is strictly less than k, again by inductive assumption, the set a1 A2 dot 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 and so on is infinite. Okay, and hence the set is set S is also infinite. So this implies basically the set S is also infinite. Okay, so now the next part where the main the difficulty is in the next part where we would consider that assume that a naught is not a perfect square. So a naught, which is of the form 3k plus 1, is not a perfect square. So then what we can say is that there exists L greater than equals to 2 such that 3L minus 2 whole squared is less than 3k plus 1 and would be less than 3L plus 1 whole squared. Okay. So again, why? Because we are like again, if we are if this 3k plus 1 is like if you are adding the next term would be, if 3k plus 1 is not a perfect square, then the next term would be plus 3. Okay, so the remainder under modulo 3 remains the same. Okay, and so that's why again, as in the first step, we took the two squares. Here also we are taking the two squares which are giving remainder 1 under modulo 3. Okay, so now let's come to the thing, that is, since 3L plus 1 whole square is equal to 9L square plus 6L plus 1, which is 3k plus 1 plus 3L square plus 2L minus k. So there exists the smallest m greater than equals to 1 such that 3k plus 1 plus 3m is a square. Okay, so there exists a smallest m greater than equals to 1 such that this 3k plus 1 plus 3m, this part here is a square. Okay, so it basically means that a1, which is 3k plus 1 plus 3, that is 3k plus 4, am minus 1, which is 3k plus 1 plus 3m minus 3. So it's basically boiling down to 3k plus 3m minus 2, and so on. Am would be 3k plus 1 plus 3m, which would be basically p squared, and am plus 1 would be equals to p. Okay, so now if p squared is less than 3l plus 1 whole squared, then p is equal to some 3s plus 2, as the first square of the form 3s plus 1 whole square, like let me write it down, as the first square of the form 3s plus 1 whole square, that is bigger than a naught, is 3l plus 3l plus 1 whole square. Okay, and by step 2, the set am plus 1, am plus 2, and so on is infinite. Okay, and hence the set S is also infinite as well. And if p square is of the form 3l plus 1 whole square, then am plus 1 is equals to p is equals to 3l plus 1. And now note that 3l plus 1 is less than 3l minus 2 whole square. And so this inequality is equivalent to basically 3l plus 1 is less than 9l squared minus 12l plus 4, or basically 5l less than 3l squared plus 1, which is basically true for L greater than equals to 2. And so we have 3L plus 1 is less than 3L minus 2 whole square is less than 3K plus 1 for L less than K. And now again, by the inductive assumption, the set am plus 1, am plus 2 dot dot is infinite. And thus the set S is also infinite. And thus we have proved our claim, that is, okay, so here our claim, that is S is finite if and only if A naught is divisible by 3. Okay, so yeah, so there are some minor inequalities which I have said here, so just go and verify them if you are not convinced. And yeah, so if I go on solving everything with those basic inequalities, so again, I mean, it's already the solution is lengthy, so it will get further, the length will increase, so let's not do it. So yeah, do some verifications from your part as well. And yeah, so finally we are done with the problem. And yeah, the last problem and the toughest one in CMI 2023. So this is it for this video, and thanks for watching, and keep watching and keep learning. And that's it for this video. Again, I'll be posting the other videos of the other solutions as well, so please do stay tuned. Bye, see you in the next one.